So last time we looked at the main components of a vapor compression cycle. We're going to get a little more in depth there, but just as a recap, the vapor compression cycle is a refrigeration cycle that accomplishes some cooling in some zone or space, and it uses these pieces of equipment mainly to accomplish that vapor compression. So it's called vapor compression. It uses the compressor and expansion valve and two coils to take vapor at the compressor stage, condense it down to a liquid, start evaporating it at the expansion valve, fully evaporate it at the evaporator when it picks up the heat from the zone, and then starts the cycle back over again. So as we look at the next couple slides, we're going to have this quad chart kind of layout where we're looking at the picture from the field about what this equipment looks like, the different components and where we are in the cycle, the saturation phase and chart and where we sit there, and then just the schematic that shows the basic layout. So we're going to start with the compressor. So in a simple DX type split system, it's going to sit in the condenser, and it's typically going to be a scroll type compressor. And we'll get into the different compressor types and what they look like, the guts of them, in the next couple sections. But for right now, we just acknowledge that it sits in the condensing unit, separate from the condenser coil, and it's responsible for taking in work into the system to pressurize the refrigerant vapor and send it on its way throughout the rest of this loop. And you can see on the saturation chart that we're going to see a little bit of an enthalpy change from the heat that's picked up, and we're going to see the pressure get to the constant pressure line that we see it go at across the condenser process. So the compressor spits out into what's called the hot gas line, and you can see it represented here in both in the schematic and in the condensing unit. So from the hot gas line, it's going to go into the condenser, which is a short trip in this case, and then that condenser coil is going to have that indirect air to vapor heat exchange with ambient conditions with this fan to help get more CFM and get more of a heat exchange. So we can see it on the saturation chart here as a constant pressure process, but we're going across the vapor dome, which means that we're going from a vapor state and we're ending up at a liquid state. So now we're going to have discharge into the hot liquid line. So you can see this coming out of the back of the condensing unit, and that's one of the lines that goes into the space. It's going to be an uninsulated line that's going to go to the expansion valve that's going to be in the evaporator unit. So here we see an example of what that valve looks like. So typically an expansion valve or thermal expansion valve is going to be either electrically controlled, or it could be a pinch in the pipe, or it could be a little valve needle here that's manually set. But its job is to maintain low evaporator pressure. So it's a big pressure drop that, as you see on the chart, at constant enthalpy, because there's no heat exchange here, is going to drop the system pressure down to where it's going to sit at the evaporator. And when you do that, when you drop that pressure down, because of the way that the properties of the refrigerant, that's going to accomplish this temperature cooling, so that the refrigerant in the evaporator is going to be at a much cooler temperature. So now there's a small line where the expansion valve is discharging into the cold liquid line that's going to go right into the evaporator. So the evaporator is another coil, and in this case it can be considered a liquid to air indirect heat exchanger, and that's what's going to suck up the heat from the zone or from the space, typically with a fan, again to help with the CFM and help the heat exchange. But it's going to capture that zone load, and as it does that, it's going to boil or evaporate. And on the saturation chart here, you can see that it's at a constant pressure. It's leaving the vapor dome, and it's going into that vapor state. And it does that discharging into what's called the suction line, which is this line going into the inlet of the compressor, and you can see that it's insulated, and one reason that that's done is to protect the compressor. The compressor only wants to see vapor. Pumps are for liquids, compressors are for gas. So if there was any type of heat exchange at that suction line, such that there was a little bit of liquid getting into that compressor, it's going to cause damage. So we insulate it to protect the compressor. So this is going to be a cycle that is going to be common to all vapor compression devices and systems. And chillers, as we said, are internally housing this refrigerant loop. So when we look at DX coil, it's a split system. Half the refrigerant loop is inside the space, half of it is outside the space. But in a chiller, that loop and those four main components all sit inside the piece of equipment that we call a chiller. And then it's got these intermediate loops for chilled water that runs out to the space to a coil, and either an ambient air condition or condenser water to a cooling tower. But we're talking about the same equipment, but instead of an evaporator coil, we have an evaporator barrel, which is, as we saw in the heat exchanger section, is an indirect liquid-to-liquid heat exchanger device. In addition to the four major components of the vapor compression cycle, you might notice that looking at something like a chiller that it's a little more complex than this. So we're going to cover a few other components that you may see looking at this system, so you can kind of be comfortable with the configuration that you're looking at and understand what some of the operation and performance implications might be. So the first thing that you may notice is that the thermostatic expansion valve may not look quite like what we have pictures, and it might look more like this. So one of the components that's common in something like a chiller arrangement is this temperature probe that's going to have a bulb that's going to run all the way to the evaporator. And what it's doing is measuring temperature, because as the temperature gets lower, that's an indication that you're in low load. And what the expansion valve can do is actually have that temperature change be registered and change the pressure on the valve, and it'll move something like a needle inside the expansion valve so that it can change the flow of refrigerant going to the evaporator. So it's essentially a way to automatically regulate the flow as loads change to the evaporator. You might have something like a sight glass on that liquid line upstream of the expansion valve, and it'll look something like this. So the idea there is that you can look in there and quickly determine, either through some color change or through bubbles, if you have some type of leakage with your system or if you have moisture in the system. And that's just a quick way to kind of check the health of your refrigerant circuit. Next, you might see in that area a solenoid valve or something that looks like this, and that's essentially an electromagnet or electromechanical valve that is going to isolate this line. So it's essentially a binary open and close, and what it's going to do when energized is just fully open, let refrigerant go through, but when the compressor's off and the system's off, it's going to fully close. And the intent there is that you don't have refrigerant that is going to migrate through your condenser towards your compressor and have a condition called slugging, which is when you have liquid real close or right at the compressor. When that turns on, that compressor is going to bang against that incompressible liquid and almost consider it like a water hammer situation, and that's going to cause a real loud mechanical bang, maybe vibration, and it can damage your components or blow out some of the seals in your refrigerant line. Next, right there, we might have something like a filter dryer. So it's essentially a desiccant that's going to try to capture any water that may be in the system. And if you don't capture that water, you could have not just capacity loss, but you could have some acidic compounds forming in your refrigerant circuit. And then pretty close to the discharge of the condenser, you should have something like a receiver. And this is essentially just a holding tank, might look like this, that is going to capture excess refrigerant. So in that low load condition, when you're restricting a lot of flow through your expansion valve, you can have excess refrigerant, and it's going to be kept in this holding tank. You might have pressure gauges, something like across the compressor, a way to read the pressure change and assess the performance of the compressor. And then the last thing that we'll talk about is this hot gas bypass. So what this essentially is just a bypass where instead of going through the heat rejection of the condenser, the liquid phase change through the expansion valve, you're going to have a bypass where hot gas can go right from the compressor discharge into the inlet of the evaporator. So why would you want to do that? So you can imagine that that's tantamount to false loading your system, and instead of rejecting heat, you're now treating that heat in your evaporator and through your compressor. Well, the idea is that when you're in a really low load condition, instead of short cycling, so having your compressor turn on and off, which can be a problem for a number of reasons, but of note is where you might not have enough lubrication running through your system, because the refrigerant will contain a certain amount of oil in a system like this. And with that on-off condition, you might not distribute that lubrication through your system, causing some early component failures. And also, if you're in a really low load condition, you might have temperature drops at your evaporator such that you could have frosting or even flooding at the compressor. So it's really an equipment protection feature. But when it runs, it's going to have a lot more energy usage associated with the chiller. So one of the things that you may want to do, where you see a solenoid valve like this and a thin bypass line at the discharge of the compressor, is throw something like a portable data logger with a temperature probe. What you can do is take something like a sponge or a spongy material, and you can wrap that temperature probe right against the discharge of that solenoid valve, zip tie it maybe, and then over time you can watch and see how much that hot gas bypass is used. If it's a lot, that's going to really affect the performance of your chiller, indicate that you may have a sizing issue with the typical loads that you see, and you may want to investigate some different ways to handle that low load. Something like a buffer tank, or using the thermal mass in the system to stretch out the cycles of your chiller. And as we get away from HVAC fundamentals, that's kind of an approach that we're going to want to take with us, is now that we understand a little bit more about the fundamentals of these systems, what the components look like and how they're put together, what the equations are that govern them, we're going to want to think about what points of contact we're going to need to have with these types of systems in order to determine or assess what their performance is. So with that, we're going to move on to looking at some typical HVAC heating configurations, but before you move on to that, there's a link in the comment section to take you to some practice exercises that will reinforce what we've learned looking at these cooling systems.